Okay, our next lecture is going to be about indefinite integrals. We are also going to have a short discussion about the so-called Net Change Theorem. Okay, what's the first item? Indefinite integrals. In the last few lectures we have been talking about antiderivatives of a function several times, and we have utilized several notations for it. Now we are going to go toward the official notation that you are going to be using from now on. So the main issue here in this section is a notation for antiderivative of a function. We have gone through several stages. Very first time we came across this issue, we used a very crude notation looking like this. We say, what is the function that if you differentiate it you get say 2x, and the answer we would write that missing function, the one that if you differentiate you'll get 2x, is say x squared, and then we realized that any constant added to it would not change anything. That's how we would answer the question. Of course, using a question mark is not going to look very professional. We went on and had another notation. So suppose the derivative of some function is 2x. What is that function itself? So answer would be x squared plus c. So that was our notation number one. Then we came to notation number two. Well, that is fine so long as you're willing to allocate a name for every little thing you want to find antiderivative for it. So sometimes we had reason to name our functions, and that brought us to the third notation. Sometimes I would say there is a function 2x. Who is the antiderivative of it? We would write the antiderivative, so x squared plus c. So implication here was that if you have a lowercase for a function, the uppercase of the same letter is going to be used for the antiderivative. So f prime would be same as f. Now we are coming to the fourth and the final notation for antiderivative, which is the following. If I intend to take the antiderivative of a function, I just use the integral sign followed by the function itself followed by the differential of the variable I'm working with, and then the answer will be written as what it was in any of these three prior cases. I write x squared plus c. Why do we use this notation that was previously used for definite integrals? Because of the interplay between a function and its antiderivative, it's very suitable to use that notation here, except that you notice that we don't have any lower limit or any upper limit. So without lower limit and upper limit, the integral notation indicates that you're finding the antiderivative of your function. Let's go ahead and practice this thing. Suppose I ask you to find the antiderivative of x squared plus 3x. So find antiderivative of this function. Maybe I better go ahead and write it better than this. Find antiderivative of x squared plus 3x. How do we write our answer? We say, if you want to take the antiderivative of x squared plus 3x, you just go ahead. Now you perform whatever rules you have learned. Antiderivative of x squared will be x cubed over 3. Antiderivative of 3x is 3x squared over 2. And we don't forget to put our constant. So that's going to be one of your major preoccupations for one section here. And then at the beginning of Calculus 2, you'll spend a huge amount of time just going through all sort of problems related to finding antiderivative or indefinite integral. Let's go ahead and practice the kind of functions we know how to find their antiderivative. That's going to give us an opportunity to practice notation. So what is antiderivative of x to any power n dx? Here, of course, understanding is that n is constant. Well, we know what the rule is, just as what happened here. We have to increase the exponent by 1, divide by the new exponent, and add a constant. We remember that this is not going to work if the exponent is minus 1, so we put a restriction on it. What if n was equal to minus 1? X to the power of minus 1 dx, written in a more civilized way as dx over x. Well, as we go through this list, I hope you come along and try to answer each of them by going through your memory and trying it out. Make sure you made the right guess, and come back here and check your answer in each case. Well, this one is the natural log of absolute value of x plus a constant. So that is another formula we are familiar with. Another one is exponential of x dx. That's the easiest one. Antiderivative of exponential of x is just itself. So among all the formulas, that stands out. The function and its antiderivative are the same. Then you had a whole list of trigonometric functions. What's the antiderivative of cosine of x? You are looking for a function that if you differentiate it, you get cosine back. It's very important for you to practice these things and make sure you do not confuse the operation and its inverse. We are not taking derivative of cosine. We are asking, who is it that if I differentiate that, I'm going to get cosine? And the answer is, of course, sine of x. How about the sine of x? The antiderivative of that is cosine of x plus a constant. Minus cosine, because derivative of cosine itself gives birth to a negative, and this negative is going to cancel that, and we are going to end up with a positive sine of x. What else did we have? We had, of course, secant square of x. Do you remember what was the function that if you differentiate you get secant square? To practice these things, of course, it's tangent of x plus a constant. Another function that you have seen, secant of x, tangent of x dx. Would be a good exercise to take that and differentiate it from scratch. Write it as sine over cosine, differentiate, make sure you see that that comes about. Then you memorize it backward. We are really not telling you how to go about going from the left hand side to the right hand side. It's just that by memory that you are going to do these things, and that's the challenge. As we consider more and more complicated function, it becomes less and less clear as to how to go from left to right. So for these very basic ones, it's very important you practice them very often, so that you can answer each of them in less than a couple of seconds. And then when it comes to the complicated ones, you will be able to go through all the maze that you need to go through to get the answer. Here, antiderivative of secant tangent is, of course, secant of x plus a constant. Now you have the other side of the coin with all of these things. Of course, you have for cosecant square of x, you remember that if you have cotangent, the derivative of it would have been minus cosecant squared. So if you want cosecant square, start with minus cotangent of x plus a constant. If you want cosecant of x cotangent of x dx, antiderivative, again, if you had started with the cosecant, you would have ended up with the negative of this. So you need to start with negative cosecant of x, and then you will have that function back. What else? We had inverse trig functions that gave birth to lots of interesting formulas. One of them is just this, dx over radical 1 minus x squared. What's the function that if I differentiate, I'm going to get this quantity? And that is, of course, sine inverse of x plus a constant. You remember there was actually another option you had. Perhaps we don't need to make our life any worse than what it is, but just to remind you, cosine inverse of x would give a derivative which was negative of this. So if I start with minus cosine inverse of x, I also get that answer. What else did we have? We had, of course, dx. We had 1 plus x squared in the denominator. That was derivative of what? That was the derivative of tangent inverse of x. Of course, you could also write it minus cotangent inverse of x, but let's stay with just these three basic inverse trig functions. The other three are a bit problematic. In different books they have different definitions for them, and this is more than enough for what we have in mind. Make sure that my ones are readable as ones. This is also 1. That is obviously 1. Let's go ahead and just pick a few problems and work them out and see how it is going to be done in this section. Let's say, so here are some examples. What is the antiderivative of 1 minus t times 2 plus t squared dt? Well, this is not a hard problem so long as you don't make a bad mistake in it. When you want to calculate the antiderivative, you have to make sure that certain common mistakes don't happen. For example, if you have two functions multiplied with each other, you cannot go take antiderivative of each part and then multiply them later on. For example, let me start by like this. Suppose somebody sees t times t dt. Could I go ahead and do this? And let me give a big warning ahead of time. No, you cannot do like that. You cannot go take antiderivative of t and take antiderivative of the other t and do something with respect to constants, whatever you want to do, and expect this will be the same as that. No such thing applies. Just go ahead and check this. If you multiply t times t, it's t squared. Antiderivative of that is t cubed over 3. Has nothing to do with whatever you have here. So we cannot take antiderivative in a piecemeal fashion. The only time we can do that is when you are adding or subtracting two functions. But division or multiplication or exponentiation doesn't allow you to do that. So what is to do here? What we do is just like that. You have to multiply it out. If you can, just multiply it out. 1 times 2, 2 times minus t, 1 times t squared, and then t cubed. Now we just go ahead and do the job. Remember, if you are using certain letter here for your variable, write your answer using the same variable. Be careful about this, not to mix and match your variables. Antiderivative of 2 is just 2t. Antiderivative of 2t, just t squared. Antiderivative of t squared is t cubed over 3. Antiderivative of t to the 4 is t to the 4 over 4. And then you throw in a constant for good measure. Some problems will give you a run for your money. You have to just work on them, challenge yourself to do these things. Here's another example. Sine of x over 1 minus sine square of x dx. I'm writing my signs two different ways. Let me correct my handwriting. Well, nothing directly looking like this shows in our table. We had this long table. We might as well go give it a name. This is a basic table. There are tables like this, as thick as your calculus book. The entire book is just tables like this. So that gives you an idea how complicated the whole thing is in comparison with differentiation. For differentiation, you had a half dozen rules, and that was it. And whatever function you had, you just follow it and you get your derivative. But in these cases, we have a lot more work to go through. At any rate, this function that we are facing doesn't show up in that table, and here the challenge starts. You have to think about manipulations of this such that you break it up or make it look like some item that is in the table. So what do you think you can do? You have to think about modifications that can be made here. You want to think about it for a couple of minutes perhaps and come back and then see if your approach was correct. Yeah. I go ahead and perhaps you pause and come back. Sine of x, 1 minus sine squared. One approach we might take is that we remember from basic trig identity that the 1 minus sine squared is equal to what? That is cosine square of x in dx. Now, you could again notice that this doesn't directly appear in that table. If you think about how can I make it look like something that I had over there, perhaps you think about this. Let me separate it into pieces. Again, you perhaps don't memorize it in that fashion, but sine of x over cosine of x is same as tangent of x, and this is just secant of x. So now we can go ahead and ask ourselves, what's a function whose derivative is tangent secant? And do you remember what function it is? Tangent secant. Now it showed up in our table. It's same as secant of x. So in this problem, we went through some trigonometric identities on the left-hand side until it looked like something that we have seen. why go through this as opposed to some other maze? The best answer I could give you is just keep practicing these type of problems until you get the knack of it. The formula you're looking for that will immediately take you from here to the right hand side, in a sense, doesn't really exist. While there are some general theorems, fancy software that will do that, but there isn't really anything that will substitute just practicing. Let's go another example. Here's another example. Sine of 2x over sine of x. Now this is a bit trickier because you have to remember a trig identity. Many students don't remember. What is sine of 2x? Do you want to pause for a moment and come back? Sine of 2x, that was 2 sine of x cosine of x. So this is really just 2 sine of x cosine of x divided by sine of x dx. Now the cancellation makes our problem very easy, because all I have is 2 cosine of x dx. And you remember the linearity rule for antiderivative. You have a multiple, that multiple just stays there. This is 2 sine of x. Antiderivative of cosine is sine. You just double it, and then you constant. You don't need to double your constant. That's just still another constant. There's no point in doing that. Here are some other examples. Suppose you have x radical x dx. What should we do here? What formula do we have that will work? Try it for a second and come back. So x radical x, I combine it as x times x to the power of a half dx. That's obviously x to the power of 3/2 dx. That is going to be, we learned, increase the exponent, divide by the new exponent, and add a constant. So 2/5 of x to the power of 5/2 plus a constant. If you don't like the look of this type of powers, 2/5 of x to the power of 5/2. I can extract x squared out of it. This is 2 plus a half. That's a 2 and that's a half plus a constant. Once you practice enough of them, then you can move on to the problems where a definite integral is asked from you. Find the following definite integrals. For example, here's a question. Say 3u plus 1 squared du. Integral is from -2 to 2. So this is a definite integral. We have definite start and ending point, as if some function had been drawn, 3u plus 1. Like you had the u axis here, you had 3u plus 1 squared, some function, and then you are going from -2 to 2, and you are trying to find that area. You're trying to find this area here. So you're not finding antiderivative here, you're finding an area. How do you go about this? You said by the fundamental theorem of calculus. You can write the antiderivative of this, and then evaluate it at 2 and minus 2 and subtract. To separate the two processes from each other, for a moment we just put aside these limits. I go after finding the antiderivative. So first time around we come across these problems, we break it into pieces, find antiderivative first. So I don't have to carry these things all over the place with me, make the whole thing cluttered and not getting anything out of it. So I go ahead and answer that. Well, how can I answer it? Really, this by itself does not show up in our table. Don't think about making this cube divided by 3. That's going to be incorrect. That would have been right if you had just plain u squared. There's no reason that should apply here. So what do we do first? Apply algebra. Open this thing up. It's 9u squared plus 6u plus 1. So far I've just done algebra. I open this thing to get that. All of this. Now I take my antiderivative. 9u cubed over 3. 6u squared over 2. Antiderivative of 1 is just u, and then if you wish to insist on a constant, that is fine. Now this is 3u cubed plus 3u squared plus u plus a constant. Now we port that answer here. That is the antiderivative. So we write the antiderivative. 3u squared, maybe I rewrite it down here, from minus 2 to 2. 3u squared plus, 3u plus 1 squared du. I copy this through. 3u cubed, 3u squared plus u. There's no reason to put a c there. Let me remind you, just putting and see what happens. Now we set the two limits. We've just ported through here and remind ourselves the two limits are 2 and minus 2. Now I go ahead, plug 2 in this. That is, I write 3 times 2 cubed plus 3 times 2 squared plus 2 plus that constant. Subtract from that whatever you get by plugging minus 2 in this. Be careful with dealing with your minus. Minus 2 cubed. 3 times minus 2 squared plus minus 2 plus a constant, whatever constant you have. Once again, we notice that our constants here play no role when we are dealing with definite integrals. The rest of it, we just go ahead and calculate. This becomes 3 times 8, 24, and a 12, and a 2. And then I have minus 2 cubed is minus 8. With this minus makes plus, so I have another plus 24. Minus 2 squared is plus 4 times 3 is a 12. This is a minus 12. Minus 12 becomes plus 2. So notice that those even powers cancel each other out. Okay, you had the 2 here, that was an even power. That's what makes it cancel out. The guys that were odd powers, if it was an odd power, it doubles up because it becomes negative of negative here. But at any rate, you just do the subtraction here. 24 and 2 makes 26, double that, 52. So that's how you would do a problem with a definite integral by using our notation from the indefinite integral. Again, another strong recommendation that these type of exercises are going to be bread and butter type of exercises for a couple of years to come. So make sure you can get them right and see your progress in that. Okay. Good luck. Well, maybe I forgot to mention one more thing. I promised to say something about the net change theorem. We really have gone through this thing once several lectures ago, net change theorem. Net change theorem simply recaptures the discussion we had, for example, related to velocities a long time ago. Remember, we said if you are looking at a problem in mechanics or in motion, you have the following concepts. You have time, you have position, let's call it, say, S. Position is some function of time. You have the concept of velocity, which we show as v of t. Velocity had a relationship to position. What was it? It was the derivative of position with respect to time, or s prime. We have acceleration. A is a function of time. That's a derivative of velocity with respect to time. So each of these come from its parent. V comes from S, A comes from V. What if we want to go backward? Suppose you want to go from V to S. Well, antiderivative of V is going to be S. Remember, V is a derivative of S. S is antiderivative of V. Well, anything has several antiderivatives, so S is one of the antiderivatives. You always have a constant that is loose. In a similar fashion, velocity is antiderivative of acceleration. How can I indicate that? For example, velocity, if I calculate its antiderivative, I'm going to get the position. If I have acceleration and take the antiderivative of that, I'm going to get velocity. To put it in a more useful fashion, if I have velocity and I calculate its definite integral from A to B, what do I get? Remember, velocity times time means displacement. If you add up all the displacements, what do you get? We had this discussion before. Adding up all the displacement, you get the net displacement. Last location minus the first location. This is an example of the net change theorem. V is the rate of change of position. If I have a rate of change and calculate its definite integral, what I get is the net change. Net change in the position of the object in this example is the position at the end time minus the position at the beginning time. Here's another example. If I have acceleration, now I can't use the letter A anymore. It's going to be bad notation, bad habit. So A and B here were beginning and ending time. This is another way of referring to two times, T1, T2. Antiderivative of A is velocity. Velocity at time t2 minus velocity, if I could write it, velocity at time t1. In general, if you have any kind of rate of change as a function of time integrated from some time t1 to time t2, if it's a rate of change of a quantity, let me just remove this, rate of change of some quantity, it's going to be that quantity at the end time quantity at the end time t2 minus the quantity at the beginning time. So these were examples of them which we have seen before, and it's being mentioned here. A similar example can be given to application in electricity and magnetism and all of those, but the concept that we are most familiar with are just these velocity and acceleration. Okay, I guess that should be enough for today. Good luck and God bless.